something that I didn't realize from my initial research, maybe this isn't the case that it is the case with all PFNs, with all prior fitted networks, with all prior data fitted networks, but it sounds like fundamental to prior data fitted networks is Bayesian inference. That's always the
Mhm.
case? Okay. So
Yes, yes. So they do compute the Bayesian posterior predictive distribution. That's what the basically that's what the optimization objective is.
nice. So there's a Bayesian process, a Bayesian learning process happening on, in this case, a transformer architecture.
Mhm.
That is very cool. And because we come across sometimes hearing that Bayesian inference is going to be useful with deep learning architectures like transformer architectures. But this sounds like a very concrete use case of it. Um, and yeah, it sounds like a powerful application of it.
Mhm. Yeah, it is super powerful because I mean something like Bayesian linear regression, you can do in closed form. So maybe I should still explain it to set the scene. So there, the prior would just be the data is just a line. Line has some axis, a line and some slope, and so you basically just want a posterior over these two parameters, and um, yeah, if you you do the math and you can compute this Bayesian posterior predictive distribution in closed form. For lines, this is fine. For Gaussian processes, for example, it is also fine. But once you go a step further, for example, a Gaussian process where you don't know the hyperparameters, then you have to do Markov chain Monte Carlo or variational inference. Um, or once you have a neural network and you want to be Bayesian over the weights of your neural network, then it becomes extremely complicated and you can do all kinds of approximations or SGLD or Hamiltonian Monte Carlo or whatnot. And it's the math is really hairy. And yeah, Markov chain Monte Carlo typically takes a long time to converge. Sort of there's a saying, while my chain is smoothly sampling, it takes a week or something like that until you get going. Um, and the other opportunity and the other possibility is variational inference, which is also often quite hairy in the math and also has approximation errors um, typically. And in contrast to that, prior fitted networks are just so incredibly simple. All you do is you sample from your prior, you get a bunch of lines, and then you feed these lines as like data points from a line and another data point from the line as a test distribution, as a test example, and you want to output the true predictive distribution for that data point that is the optimization objective for that one line, and you sample millions of these lines and just learn over millions of these lines by just standard supervised learning to predict the missing values, and naturally you learn to actually compute the predictive distribution because, well, sometimes typically there's noise in this data, etc. And since we optimize with cross entropy loss, if we're far off and certain, then that's bad and that's penalized. So you actually automatically learn something that is yeah, regularized to be exactly the right thing to be predicted. Um, if you sample arbitrarily many curves from this prior that look like your that in the data sample look like your sample, integrated over all of that, you want to get the best predictive distribution, and that's precisely the right predictive distribution. So just by sampling from the prior and then running supervised learning, you learn to actually approximate Bayesian inference to an arbitrarily strong degree. And that's really powerful. And so there's a lot of applications that are outside from tabular data where this is also really cool. You could do things like for a neural network, you could say, typical Bayesian neural networks give you a posterior predictive distribution, or I'm sorry, not posterior predictive distribution, posterior distribution over the weights of the neural network, and then integrate over that in order to give you a posterior predictive distribution. But what they don't do, for example, is consider, well, which is the right architecture. They just say, well, what are the right weights of this particular architecture? But you don't know which is the right architecture to explain this data. So with PFNs, you can just say, well, I have this distribution over architectures, and then for each of the weights of the architecture, I have this distribution. You sample from it; it's trivial, and then you just get the posterior predictive distribution over which is the right architecture for this data. So you kind of do some Bayesian neural architecture search in a forward pass, which is just really cool.
Mm,
There are some
that
limitations.
that
But
is really
go
cool.
ahead.
I want to quickly. So we've been talking a lot, obviously, about priors, posteriors, posterior predictive distributions. I want to
Mhm.
quickly break down for our listeners who aren't Bayesian what these kinds of things broadly mean. And so I'm going to give a really simple toy example, and with your expertise, you can tell me what I get wrong in my explanation. But basically, if I have some so I could have a simple linear model where all that I have is the slope of the distribution and some y-intercept. So this is kind of like the simplest kind of regression model. Um, with a Bayesian approach, I could assign some kind of prior distribution to both of those variables, to the y-intercept and to the slope of the line. So I could say, based on my experience with these kinds of data, with this kind of problem, I think that there's going to be a slight slope, and I think the y-intercept will be around 0. If I'm very confident, I can assign a really narrow variance to my distribution. Or if I want to, if I don't have much kind of prior understanding of what this process should be like, what this regression model should be like, I could have a very wide distribution, which will allow these kinds of learning approaches, like you said, they're Markov chain, Monte Carlo, some kind of Hamiltonian process. There's lots of different kinds of solvers for Bayesian approaches that allow me to search gradually, like you said. It was kind of like while my guitar gently weeps, uh, while my Markov chain gently converges. What did you say?
Mixes. Uh,
Gently,
uh, yeah, well, it gently mixes. It's probably the right thing to say.
and um, and so a big advantage of this kind of approach, of this Bayesian approach, is that it allows you to incorporate prior information. You don't have to have your model be learning from scratch necessarily, although you could have it for some parameters, or maybe even all of the parameters basically learn from scratch. And then after this learning process happens for a while, like a Markov chain, Monte Carlo, like a Hamiltonian, we end up in the end with posterior distributions that represent kind of what we've learned from the data. So we start with a prior distribution that could be a highly informed prior distribution, or it could be relatively uninformed prior distribution, and then we use the training data that we have to converge upon some posterior distributions that give us so they incorporate the prior information as well as the data that we have trained on. And you were just giving lots of cool examples there where we can use posterior distributions to be finding the weights of a deep learning network, for example. How did I do?
Mhm. Yeah, no, actually, very very good. The one thing I wanted to say, we do have a limitation. Actually, we don't get the posterior over the weights of the neural network. That is what you get with standard methods like MCMC and variational inference. We bypass that step. We just directly go to the posterior predictive distribution. So the y given the x.
Oh.
And we don't have a posterior over the w, the weights. Like with MCMC and with variational inference, you actually integrate out over all of the weights in order to get your predictive distribution. But we bypass that. We can't tell you which is the right architecture, actually. We just tell you the Bayesian integral over all the possible architectures that might have explained the data.